pretty well for the last session. And yeah, thanks for coming. I just want to say, today's really the start of a new experiment for us and for you. You know, obviously this is not something we foresaw until just recently. I just want to say, I mean, I hope you can bear with us. I mean, we're really doing our best to try to make the class continue to work. But, you know, we just have to accept that things aren't always going to work smoothly going forward. And so to that end, I mean, I think really it's going to be important that we keep lines of communication open. We do want to hear your feedback. You know, let us know if something is working for you and you want to share with other people, or if something is not working for you. There's all sorts of different ways you can get a hold of us. Because really, I'm going to say some things about how we think we're going to try to do class going forward. But all this is really subject to change, because right now we're just guessing what we think might work. But if it turns out it's not working, we will rethink. And so the communication is important. We added one more solution that we didn't have in the first part of the term. So we added a Discord channel. I think a lot of people are familiar with this. So if you want to, there's a link on the slides or on the website if you want to join and use that. And so that's really for communication, not just with us. I mean, although we're on there, and and some of the TAs and the coaches will even be there to answer questions. But it's also a communication tool for you, because we want to make sure you all can talk to each other and, you know, work on things together, because that's really one of the best ways to learn in this class. And the things we're going to say, at the beginning, are going to be also on the syllabus addendum on the website. I'm just going to point out a few things, but there's like more text there and some of the reasoning. And I just realized I forgot to start the recording, because we are going to try to record, and I'm going to try to do it in chunks of different parts of the lecture, so that you can go back and look up maybe just one part and not have to watch a whole hour and 20 minutes. But more or less, so what we're going to be doing, a few other things about how this is going to work in Blackboard. So you're all here. That's good. Hopefully you can all hear me. Hopefully you can all see the slides, which should be being shared as well. And then also I have video that you should be able to switch to if you want to see me, which will be useful later. By default, I've turned off most of the sharing for all of you. The text chat is still open. If you want to type there, you can ask questions there. If you'd prefer to ask a question by voice, or you wrote something down and you want to show a video so we can take a look at it, you can use the raise hand thing like that. There's a button at the bottom of your screen. That'll get us attention. And if you leave that up, then we can give you permission to speak. Okay, yeah, so, you know, unfortunately, there's people like, that will have technical problems. You can play around with the settings. We're not going to be able to do live troubleshooting in the middle of lecture. But if you want to try out, you know, get a hold of somebody some other time, we can probably work with that if you need to play around with your settings. Otherwise, if it's just a temporary thing, like it usually works, and it doesn't work for a moment, only thing we can really try is leave and come back. Okay. There we go. Okay, so the plan. Class had been going well. Like, we were actually really proud of how everyone was doing, especially the last exam was great. So we want to translate what has been working. And so our sort of goal has been do the least amount of changes necessary to make it work as an online setting. So for now, at least, we're still planning on having live class meetings. So you're here at the live lecture, that's good. I'm going to try out recording pieces of it. We'll try out recording it different ways to see what works best. We'll also have live recitations on Blackboard Collaborate. And like we've said before, recitation is probably the most important part of this class, right? discussing, talking with people who are also trying to learn, teaching them teaching you. It's the best way to really get a handle on this stuff. So we still want you to come to these recitations live if you can and work together with other students. But to facilitate that, we are sort of changing a bit the way this organization works. Now, what we're going to do is we will have a live recitation session at every time there was a live recitation, physically before. And if possible, we would like you to come at your scheduled time because we have to assign people to help, right? We don't want 100 students to show up and have like 2 TAs and 2 coaches because you won't be able to get people to answer your questions. So if you come at your scheduled time, that's how we're going to start off assigning helpers, right? Based on essentially how many students there were at different times. But we do want you to be able to pick groups to work with because different people will communicate in different ways better. Maybe you like writing on the shared whiteboard. Maybe you just like having a video chat and showing each other your paper. Maybe you like everybody writing on the shared whiteboard at the same time. Maybe you like somebody who's the scribe and everyone else talks to them. There's lots of different ways that it can work, but we want you to work together. So we're going to let you pick groups. If you'd rather not find a group to work with, we'll just put you together with whoever else is there. But you can pick groups either from your time or from other times and move around the schedule a little bit. We'll try to be flexible and accommodate offline work. Or we'll try to be flexible at the scheduling for the TAs if we need to be. But we'd also ask you maybe to be flexible about moving to other times if possible. Yeah, we have the same TAs. At every time, it'll be one big session. So there might be a session with 3 TAs in it at the same time. I think every time has at least 2 TAs at the moment. So we'll see how it goes. But we will also try to accommodate offline work if needed. If you are 12 hours different time zone because you're in China now and you really can't make 8 p.m. Recitations, which are 8:30, which is the first one. Yeah, like we can understand. So what we would like is you to actually still do the work, maybe find your own group that you can chat with on another way, but we'll work with you. So let us know if you're having a problem about something and we'll try to figure out a solution. Otherwise, we'll still have homework. It's just submitted on Blackboard. And so for grading, if you're worried about the grading part, again, we're going to try to change the least amount possible. So for recitation, we still want to make sure you're doing it because we think it's the best way to learn. So there's still a bit of a grade attached to it as incentive. So we'd like you to submit on Blackboard. We'll make assignments where you just give a brief description, what you did. Say, oh yeah, I worked on this. You can give us feedback. Oh, we thought it was great. This was a great way to collaborate. It was a great way to talk to each other and figure out how to do stuff. You could say what didn't work. You could say what you're confused about. So let us know, but we want some feedback. And that's basically, that'll give you a participation part of your grade. No real changes to homework. Basically, you just turn it online, grade it online. The paper, short paper on the process of science is still on. I think we'll hear more about that next week. We will still have exams, but we'll have to change the format. 80 minutes all at the same time does not work online. So what we'll do, at least with the way we do exams, you can do it with multiple choice online, but not the way we do exams. So we'll probably change these to 24-hour exams. So they'll probably be a little bit more involved, but we're not going to expect you to work 8 hours on them. The main change to the grading now is we don't think the group exams as done will really work properly. So group exam 3 is now not going to be graded. And so it should be dropped from the grading total completely. We'll still have practice problems since the group exam was also practice problems, but we'll just have you work on them to help you out with studying. Okay. Now, about getting help, right? Because still, besides just lecture and recitation, we still, want to talk to people and get help. We will have our help sessions online now, replaces the old office hours. And this is going to be involved with the physics clinic. The physics clinic is not going to be on Blackboard. It's going to be online. It's going to be on this thing called Zoom, which is a lot like this. just a different company made it. The reason is that we don't have all the physics classes in one Blackboard. So that's the way Blackboard's organized. And so we made a Zoom meeting. More information's on the website, including the link. The hours will be shortened. The TAs won't be there as often, just afternoon and early evening. But that's where we'll have things like our office hours. We'll just make like a sub meeting in there that you can join. But we want you to talk to the students. Again, I mentioned the Discord. Form your own online groups, however you like to connect with people. And then, let us know. You can email us or otherwise, or any of these, the chats, if you have any issues with the tools, and we'll try to work with you and find a solution. Okay, so I saw some questions that Professor Freeman's been handling in the chat, but are there any other questions about how the class is going to work? Group exam grade B. I mean, the third group exam just doesn't exist anymore, basically. And then the way we were doing the other group exams, right, was you get the grade from the exam if you missed it, I think. So. And about the homework due date for tomorrow. So I don't know what it's set to actually at the moment. I can check that after the class. But I think I set the next one to be end of day, so it's probably end of day tomorrow, or it should be. I mean, I don't really know anything about the lab. I don't. Professor Freeman might know a bit more. Apparently, there is still a lab, but I don't run that, or I'm not really involved with it in any way, so I can't help you. Okay, yeah, there's still pre-lecture questions. That was already online, so that's not too bad. So there were some for today. We didn't have a ton of people answer them for today, but there will be more. I'll have to put them up later for Thursday, but yeah. Okay, so why don't we go ahead and move on to doing some physics stuff. So I'm going to make a new recording. Okay, so at the beginning of today, we do have a little bit of a lecture to cover some topics that kind of got squished into the end or skipped right before spring break. So this is first about power. So hopefully we haven't completely forgotten what was going on. So we start talking about work and how forces, when they act over some distance, can give you energy into a system. And usually we said, oh, this is because we don't care about the time, but there is something that still does care about how long it takes, which is power. So if you have an amount of work giving energy into the system, and that takes a certain amount of time, that gives you what the average power is, right? And this is an instantaneous thing as well, just like with motion, that this is really, the power right now is the derivative of the work that's being done. So how much energy are you putting in right now? So if you want to think about what that means, right, then really your colloquial definition for what power is actually pretty good. We use that a lot. Someplace you might have heard that is like with a car, right? The car has some engine power. It can have a less powerful engine or a more powerful engine. And what's the difference, right? Well, they'll both get you up to speed on the highway, right? But the more powerful, sports car or something can do it in a lot less time, right? So it has a smaller delta T. And if they had the same mass, it would be the same work to get up to the same velocity, right? So, and that's basically what's going on. So we had from before the work energy theorem, this 1/2 m, and then the change in the velocity squared is the work done, right? And then this is the power times the time, or really it's the integral of the power over the time. And electrical power is actually a similar thing, but we don't deal with electrical forces in this class. So you can think about that if you go on to 212, where they talk about electricity and magnetism. Okay. Also, I think we skipped a bit what the units are. We didn't actually need any new units, right, for energy and power. Energy was just force times distance, and we knew what force was, right? It was mass times acceleration, so meters per second squared. So now you have to take all these units and multiply them together to get energy, right? So you need mass, kilograms, meters per second squared, times another distance, so another meters, right? And that gives you kilogram meters squared per second squared, which is a lot to write down. So there's an abbreviation sort of for this, another unit that's just this combination. It's called a joule. So when you see a big J, that's what that means. And then for work, you just have to divide that by another unit of time. And so you get a joule per second, and that's what's called a watt, right? Which you hear a lot for electrical power, but if you're looking at car engines, maybe you'll see horsepower. This is also just a unit of power. It's actually 1 horsepower is 746 watts in our sort of standard SI units. Okay, so those are just the units so that we're not introducing anything new. So I just want to start off with an example, which is in the context of power, right? But it's also a good example where we can just remember what we were doing with work and the work energy theorem. Okay, so this is about a race car here. That's actually, I want to see how this looks. So what I'm going to try to do is actually do like we did with the document camera on the paper, so you can see the process. So what you might want to do is you might want to click the video that's in the corner of your screen instead of the slides for a minute, and you can go back and forth that way if you want, so you can see both. All right. Okay. So I have my drag racer here, right, which is going to accelerate down the track. Okay, and then we're going to think about this in terms of the power that the engine puts out to get it up to speed. Okay, and so this starts off a lot like what we did before with just work energy problems. And so one thing we need to think about is what are the forces acting on the system, and it can help sometimes to draw a free body diagram. Right, so I'm going to go ahead and do that just like we did from the last part of the class. Right, so there's a normal force. Right, there's a force of gravity. There's some big force that makes it go. Right, that's the traction of the tires actually. But there's also drag forces, right, or a frictional force which slows it down. And in this problem, we're just given how big that is. We're not going to try to figure it out. Right, and so these are the forces that act. Right. Yeah, sorry, I was looking at the strategy. I'm going to go back and forth. I was going to go back to the problem in just a second, if you're trying to switch back and forth to the slides. Yeah, the slides are there, just they don't have questions to the poll, answers to the poll questions. They're on the website. So if you'd like to have them up yourself, you can do that. Okay, right. Because now what we have to do, we have to, again, start thinking about things in terms of directions and components. But there's now a physical reason we want to think about the coordinates, and that we have to think about the displacement that the object is going under, because we want to think about the work and the energy. Yeah. If you're having a really bad video, you can try to follow along as well. I mean, it does work. I can see, I'm actually looking at exactly what is on the video through a logged in guest, and other people can see it. These aren't perfect, unfortunately. Again, just like before, we'll have pictures of these up afterwards. you can try to follow along, try to draw, this in the notes again, and hopefully we can do this as well as we can. Okay. So we had to think about this. So the main point is, okay, we need to also think about the displacement. So that as it's accelerating along the road, right, it's also going to displace with the delta x that goes in that direction, right? And so now essentially what happens is that you can ignore forces that are not in the direction of the displacement, like the normal force and gravity, right? Because they are perpendicular to the displacement, right? So they don't do any work. We're just going to worry about the components of the forces that actually do work, so they're actually along this direction, right? And so that is then the force that's making it go from the engine and the force of the friction, right? So if I want to write down the work, this is just going to be F times delta X, right? Because this force is in the same direction as the displacement. And there's also going to be a frictional force that's slowing you down, which is FF in this case, delta X. But in this case, I need to put in the minus sign, right? I mean, you can think of this as it's subtracting energy, so it's a negative work. But really, this is just like what we did with components of vectors before, where sometimes you had to put in the negative sign if it was in the negative direction. So here, the direction is for the forces, you're comparing to the displacement. So the displacement is to the right and the force is to the left, right? Then they multiply their magnitudes together, but you have to put in the minus sign. Right? And this really comes in because it's the cross product of the vector, right? Because these are really, or not the dot product of the vector. But if it's all along one direction, you can just think of it as multiplying them and you put in the minus sign because it's backwards. Then what we're interested in this case, this is the work done by the engine. So that's like W for that force. And we want the power from the engine, right? Which is just the WF divided by delta T, right? Or that means it's just F delta X over WF, right? Because we actually want to find the power. Oh, over delta T. I don't know what I'm doing here. All right. Now, the thing we know, though, is that this work is going to be giving kinetic energy to the car, right? And so the work, the total work, is also equal to 1/2 mv final squared, right, minus 1/2 mv initial squared. Right, so the work is equal to the change in the kinetic energy. And we can, now that's our equation, like we had before when we wrote down the sum of the forces and said it's equal to the mass times acceleration. So we can go through and see what we know. Well, we don't know this force, so we don't know this work, and that's actually what we're looking for with the power. We know the magnitude of the frictional drag force, and we know how far it goes, so we know delta X. We know the mass and how fast it was going at the end, so the V final, and we know that it starts off with 0 initial velocity, right? And so what I can do is I can find this F delta X, and I can use this to solve for it, and then plug that in here. So just to save some space, because I do have to write very big, and that kind of drops my space, right? So this is over delta T, and I'm just going to plug in the F delta X from here, which means I have to move this over to the other side, right? And so then I just get that this is 1/2 mv final squared plus the frictional force times the delta X. Okay. Right, so this makes sense that what's happening is there's a work done by the engine that gives you the kinetic energy you end up with, but it has to give you more energy than that because you're losing energy to another force. Okay, and then this happens over some time, and that's what power is. Okay. So that's basically that. I mean, from there, you could plug in the numbers, right? You have all these numbers, mass and velocity and F and delta X and delta T. But I will stop it there, since we should also be able to just deal with algebraic variables. Yeah, questions. Okay, so the question, can you explain why I added F delta X again? So I didn't add it again, right? It's just the same as this one up here. I just added it to both sides of the equation so that it's next to the kinetic energy part. Right? And then that's F delta X equals that, and I just plug that in here. I unfortunately have to be a little terser with the algebra, with the limited space. Okay, so it asks, can I explain where the equation comes from? So this is one of our main equations, right, for this part, that when a force is applied over some distance, right, that does work, and the work causes the change in kinetic energy, right? We went into detail of that at the end of the last week before the spring break. So I'm not going to belabor it too much other than the bottom equation. Okay, so that's that equation. I use this equation to find F delta X, right? And then the power is just this F delta X divided by the time. And so when I found this, I just plugged it in. In this case, it does, because I'm actually just trying to find the power of the engine. I'm not trying to find there is also a power from the friction. But I just wanted the power from the engine. Sorry, I'm confused. I'm not understanding some of the questions. This is the work energy theorem, right? This is what we did the last week of the class. So that's where that comes from. I ask you to check the notes on that again, maybe. If not, you can just take that as a given, right? The change in the kinetic energy is the work, okay? I'm not sure, the frictional force times delta X doesn't go to zero anywhere. So the zero is the initial kinetic energy. That's the thing that goes to zero because it starts off at rest. Okay. So I just moved this to the other side of the equation with algebra. And so that's why it shows up here. So it was negative here and then it's positive here because it moved to the other side. But that makes sense because the engine is doing more work to overcome how much energy is lost from that. Yeah. The final, I mean, this is the final answer. It just doesn't have the numbers plugged in. I don't know what it is. I mean, you can put it in your calculator as well as I can. So, one other thing about power, I don't know how often we'll use this formula, but you might see it come up somewhere. Sometimes the power is the force times the velocity. So if something is going at constant velocity, you can figure out how much power a force is doing by multiplying the force times the velocity with the dot product. So for instance, if you're at a car at top speed, there has to be a power from the engine and a negative power from the drag force, which so that the velocity doesn't change. But you can figure out like the power of the engine by figuring out the force it applies times the velocity. Okay, so that's all I wanted to do. So power is just an energy per time. So it's joules per second, which is a watt. That was on the slide earlier. Okay. All right. So that's all I wanted to do about power. So we're going to go ahead and stop that recording, and we want to talk a bit again about potential energy. Okay. So, all right. About the next concept we want to talk about is potential energy. So we've already been talking about kinetic energy, right? And how a force acting over a distance will do work that increases it or reduces it, right? One force that we know does work is gravity, right? And so that means gravity is somehow giving energy to something if it speeds it up, right? And so the question is sort of, where does that come from? And what we say is that that gravity has a gravitational potential energy that you can convert into the kinetic energy through the work, or vice versa, that you can give up your kinetic energy, slow down if you're going up until you stop, and you give that into gravitational potential energy. Right? The reason is that, as we'll see, gravity is a bit special in the way it does work, is that we can always keep track of how much energy it could have given to something. Right? And so that is our formula for potential energy. You've probably already seen in the problems that you did before, where you talked about the work done by gravity, and you talked about how that was the force of gravity, mg times the height, so the displacement in the vertical direction, the change in height you had, and that gives you a change in potential energy. And so it's just the same formula. We're just taking the exact same concept and thinking about it in a slightly different way. Okay. But when you do this, right, it's important that we're talking about differences, like, because physically, the important thing is the difference. So that's why we say delta H. So it's a displacement in the vertical direction, because we really only care about the change of the potential. Okay. What that means, though, if we actually want to sit down and write the potential at a particular point, is we have to figure out what we want to call zero. Right. And so you can pick the ground, for instance, as H equals 0, and say above the ground has positive potential energy. You could pick something high up, the top, as H equals 0, and below that point has negative potential energy. Either way is fine. I mean, this is basically just like choosing coordinate systems when we did motion problems. And it just affects the way you write it down, but it's always the differences will be the same. Right? And so just to illustrate this a bit and to sort of keep the same language, I have just a basic problem that you just throw something straight up in the air. So it's a cat toy in this case. Right? So you play with your cat, you throw this little toy, mass m, straight up in the air. So you give it some initial velocity when you do that. And you want to figure out how high does it go. But in particular, we're really going to want to talk about what are the kinetic and the potential energies of the toy at various parts of the chip up and down. Right? And so I'll draw my picture here, right? And so here's your cat. You take its toy, right? And you throw the toy up in the air, so it goes up, 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 up. And then I'll have to draw it as a little loop just so I don't draw on top of myself. So, but we'll pretend it goes straight up and down. And we just want to talk about the velocity, the kinetic energy, right? And then the work done by gravity and the gravitational potential energy at different parts, right? So to start off with, right, at the beginning, we know it has some initial kinetic energy, right? And this is just 1/2 m v squared, right? Because you give that to it. And then from the work formulation we did before, we know as this goes up, right, the displacement will be up, right? And the force of gravity will be down all the time. Right? And so that means that this will do work. And since they're in opposite directions, it'll do negative work, and it'll subtract that kinetic energy, right? Up until right at the top, right? You have the kinetic energy is 0 because it's stopped for that moment, right? Or just think about the projectile motion, right? That you get 0 velocity at the top. Right? And then we can reverse this and let it go back down, right? And as we go back down, right, you'll have delta x down. Gravity is always down, right? And so now you do positive work on the way down, and you give it back its kinetic energy, right? And so at the end, the final kinetic energy is also just 1/2 mv squared. Because you had the same force and the same displacement, except it changed direction. Right? So you start off with some kinetic energy, you go to 0 kinetic energy, and then you get some final kinetic energy. Now, what's nice about this formulation with gravity is if we can instead think about this in terms of kinetic and potential energies, and it's just a way for us to keep track of what the energy, what's happening with gravity and the gravitational energy. So I can set up and say that this is my 0 height at the ground, right? And then there's U initial, right, is just 0. There's a question for what's the overall kinetic energy of the system. So the overall kinetic energy changes. There was kinetic energy at the beginning, it goes to 0, and then it comes back. Right? And that's what we're trying to do. We're trying to look at what is going to be the same all the time. Right? So there is a potential energy of 0, but at the top now I do have a gravitational potential energy, right, where U is just mg times the height at the top. Right? And then at the end, again, I'm back on the ground, and so UF is also 0. Right? And so there's 2 ways you can think about doing this problem. Right? So one is the work way before, that you say the work done by gravity was minus mgh on the way up. Right? And this is equal to the change in kinetic energy. Which was just 0 minus 1/2 mv squared. Right? So that's the way we would have done it last week. But we can instead rearrange this in terms of putting the kinetic and the potential together, right? And we can say instead that the kinetic initial plus the potential initial is equal to k plus u. Right? And so the kinetic initial was 1/2 mv squared. Throw this up a little bit. The initial u was 0, the final k was 0, right? And so then this is equal to just mgh. Okay, so this is the exact same idea. There are just 2 different ways to write it down. Right? That one case you're talking about the work done by gravity, and that's sort of the way we phrased things before. But instead, you can think of gravity itself as having some energy, some potential energy, right? And you add up the kinetic and potential before, and the kinetic and the potential after are the same. There's a question, why is there a minus mgh? This is the work done by gravity, so it has to be negative. Right? Because you started off with kinetic energy and you lost it. So you're losing energy. But the other way to see it is that the delta x, the displacement is up, is positive, and the force of gravity is down, is negative. Right? So they're opposite directions. So you put in the minus sign. Right? And so, again, these are basically the same way. It's just now we're going to instead call the energy in gravity to be the potential, and you add it up, and you talk about before and after, kinetic before, potential before, kinetic after, and potential after. And then you get the same thing. So one of these is minus mgh is minus 1/2 mv squared, and the other is 1/2 mv squared is equal to mgh. And either way, if you try to find h, right, the m's go away, right, and you just get that h is equal to v squared divided by 2g. So any other questions about this? The question was, is the right-hand side of the equation when the ball is falling down? No, so actually in both equations, I'm just talking about the up part. So in the first equation, we're talking about something like the work done while going up is related to the kinetic energy before to after, or after is up, the change. In the other case, it's the initial is on the ground and this is the top. I used F for the final on the ground again. So with no subscript, it's at the top. Yeah, Jason, that's what the equation is. So that's talking about this 0 is the K at the top, which is 0. So this is comparing the top to the ground. All about going up. So from the ground to the top, going up. Okay, so just to put that back into perspective. So this was, I hope, trying to motivate why we're doing it this way, but we can write this specifically. So I had a question on the pre-lecture about this. Again, this is just the same trip as basically the pre-lecture question. You started in one place, you took some path, and you ended up in the same place. Gravity is a conservative force, and so it's only affected by conservative forces. And so while the kinetic went away and you gained potential, so they each individually changed, right? They're both the same at the end. And so this idea is called conservation of really mechanical energy, although we'll usually just say conservation of energy for expediency. And that the idea is that the sum of the kinetic and the potential, right, is going to only change if there's non-conservative forces that are doing work on your object or system of objects. There can be more than one object, right? And so non-conservative forces are things that aren't gravity and aren't the spring force that we'll talk about in a bit. So things like friction is non-conservative. So if friction does work, it takes away energy from the system. Tension and normal force are also going to be non-conservative. So if they are doing work, you have to figure out how the energy changes. But a lot of times, even if those forces exist, right, we saw that they do no work. Yeah, the beginning and the end, they're the same, right? So the sum of the two is the same all the time. And individually, they'd be the same at the beginning and the end if you got back to the same position. Right, that's the example for gravity. So the example for gravity is just that you have 1/2 m initial velocity squared plus mgh is 1/2 mv final squared plus mgh final. And right, and again, this is just like doing work. It's just really a rearrangement of the work and keeping track of the energy in gravity. A similar question for the pre-lecture 3 was there. If there's, again, none of these dissipative is another word for non-conservative, in this case, like friction, then the object's total energy is conserved. Most people got that right. The next most popular answer had a decent fraction, which was that the object's total energy is always conserved. Now, the point is that it's talking about the object's total energy. So the object can lose energy if like frictions take some away. That energy does not disappear completely. It goes off into heat in that case, right? But the object has lost it, right? It's not keeping track of it anymore. Okay, so next what I want to do is another very similar example about gravitational potential energy. And you've basically done this problem if you've already finished the homework. Something very similar already. So I just want you to think about it instead of as work in terms of doing potential energy. Right? So if you have this pendulum, right? So the pendulum has some mass m, and there's a string, and you know how long the string is. So we said it's 1 meter. And if you pull it back so that you get this angle theta of 30 degrees, we want to figure out how fast it's going to be going at the bottom of the arc. And we want to think about this in terms of kinetic and potential energies, okay? So why don't you first take a minute to think about it. Think about how you would get started. And then we'll probably come back, talk about it a bit, and then let you think about it again for another minute. I mean, so just like, and again, just like in real lecture, hopefully you actually have a notebook or your paper there that you can work out some problems, because we still want you to think about stuff. Okay, so hopefully you've had a chance to think about what you would do. And in case you were getting a little bit stuck, some people might have already leaped to the end, but I want to go through this slowly, uh, how you would start off thinking about this. Now, given the context, you can probably guess we're already going to want to think about energy, right? We don't care how long it takes for this to swing. We're just talking about before and after. And so we should first probably figure out, can we talk about energy conservation or not, right? So we should go and we should think about the forces. Right, so we did force problems before, so hopefully this isn't surprising, right, that you have gravity down. The only other thing touching the weight is the string, right, and so you have some tension that's up. Right, and so the question is then, as it swings down, I'm going to make this a poll. Does the tension do work? Why don't we just take a few more seconds if you're still thinking about it. All right, 3, 2, 1. All right, let's take a look. All right, so no was the popular answer by a good margin. So no is good, no is right, but let's go through why that is, because there's definitely some that aren't sure, right? So the tension's there. You have to think about which direction is the displacement, right? So in this case, that line, right, is the tangent to the circular arc that the pendulum is going to make, right? And the tension is always along the radius of that circle, right? Because it's making a circle shape, right? And so that means the displacement is always along the tangent, right? And at any moment, right? So delta x is going to be like that, right? And it's going to be always perpendicular to the tension. So because they're always perpendicular, right, you can't get any work out of the tension. So it can't give more energy. All the energy it's going to get to go speed is all going to get speed is all going to come from gravity. Okay. Right? And so since the tension is the other force that we had, the tension doesn't do any work, right? So you can't be gaining or losing energy from that. The only other force we had is gravity, right? So, and gravity was a conservative force, right? And so that means, right, that energy is conserved. Right, which in this case means that, right, the kinetic initial plus the potential initial, right, is equal to the kinetic final plus the potential final. Or the potential in this case is the gravitational potential. Okay, so what I want you to do, especially if you were kind of stuck on this before, see if that helps and if you can reason out how to proceed to the end of this problem. Take another couple minutes. Yeah, for clarification, there was a clarification question. Is the system starting at rest? Yeah, so you pull it back and you're just going to let it go. You're not going to push it or anything. So at the initial bit, you just remove your hand. So it was starting at rest. So there's actually not really a diagonal force arrow. That's not a force. That's just thinking about the displacement direction. I know that one, sorry, that one is a little small to read. But we were talking about why the tension does no work. So the question is, is it because the string's distance from the ball doesn't change that it doesn't do work? Yeah, sort of, right? Along the direction of the string, you never are pulling it in or letting it go, right? So there's never a displacement along the direction of the string. I guess that's a way to think about it. Okay, so why don't we just go ahead and go through the solution. Hopefully you've had some time to think about it and get an idea of where this goes. Right, so we figured out what we wanted to do for the problem is that we wanted to use that the energy was conserved. When we talk about the kinetic and the potential, so we have to put them all in, right? So we mentioned this was at rest, right? So the initial kinetic energy is 0, right? Because it's not moving. So then for the potential energy, we need to figure out what number we're going to call it. So we need to pick a 0. So I'm going to go ahead and pick that h equals 0 is at the bottom position. So that means that the ball starts off at some height above that, and so it has to have some gravitational potential in the initial. And so that's mgh, where h is that height that's on the slide, actually. The height that it's raised, which we'll look at again in a second. Right, and then this is equal to the final kinetic energy. So at the bottom, it will have some 1/2 mv squared, for how fast it's going. Right, and then at the bottom, the potential energy is going to be 0 because that's where I picked the 0 for my height. Right, and so you're just taking that gravitational potential energy of mgh and converting it into kinetic energy of 1/2 mv squared. Right, this is just like what we did with the work problems. I haven't found the height yet, actually. I was about to do that in a second. This is just like we did in the terms of work, except we just sort of rearranged it and thought about it as an energy conservation problem. And the final potential energy is 0 because I defined it to be the 0. I said, oh, I'm going to pick a coordinate for my height and say the 0, and I'm saying the 0 is when it's at the bottom, so the final. So by definition, basically it's 0, and then you have some positive potential energy at the beginning. You could have done the reverse. You could have put the 0 at the beginning, so everything would have been 0, and then it would have had some negative potential energy at the bottom. But you would get the same answer. I do need to figure out what the height is, right? So I actually do need to do a bit of trig here, and so that this is the triangle where L is on the hypotenuse. This is theta. H is actually this height. And so what I have to do is I actually have to find this height, which is L cosine theta, and I have to subtract it from L, right? So it's L minus L cosine theta. Right, and so if you just do this, you want to find V. So you have to, so the masses go away. It doesn't matter. So you get a 2gh is V squared. So you should get something like V is, I'm going to go ahead and do the square root. And it's 2g times L minus L cosine theta. In terms of what number, if you really want the number, there are a lot of people trying to put numbers. Okay. Well, L is 1 meter, so it's just a 1. Cosine theta for 30 degrees is what, like 0.866? So it's like 0.14 times 10. It's like 1.4 times 2. So this is like square root of 2.8. Is that right? Something like that? Okay, so a couple questions. Do we assume the energy didn't lose throughout the motion, so the pendulum never stops? So we know the energy is not lost, that it's conserved, because the only other force in the problem is the tension, which we decided does no work. Okay, and the gravity is a conservative force. It has a potential energy, and so we can write down the potential energy for gravity. right? And so that's why. So it's just, all that happens is you convert the gravitational potential energy into kinetic energy at the bottom. Okay. And people are still confused, I think, about the height. So I'll draw this bigger. Right, if this is a pendulum and the length of the string is L, then this height is also L, right? Because that's just how far down it is at the bottom. But the height, it goes up, is not L cosine theta, right? L cosine theta is this height. Right? It's the height from where it is when it's pulled up to the top of the string. Right? And so what we actually want is this height here. From the bottom to where it was pulled up. And so that's this height, right? And so that's all L minus that height. And then that gives you that. So that's L minus L cosine theta. Okay, let's see. Any more questions then about that? Okay, so why don't we go on? I want to talk a bit more. There's one other force that we haven't spent much time on yet in this class, but it's really nice because we can also define a potential energy for it. Wait, sorry, what is an equation sheet? I'm not sure what an equation sheet is, right? You can make your own equation sheet based on the equations you need for the, you'll have all the solutions for everything. So, okay. Yeah, so the pre-lecture question one, most people got it right. There's another force that we can write down an expression for the potential energy. That's the spring force, right? We haven't done much with this yet in the class, but hopefully they're at least somewhat familiar, right? Springs don't want to be stretched or compressed. So if you stretch them or compress them, they exert a force that tries to go back to their original length. This is called a restoring force. Okay, sorry, I just want to address this. Everyone's saying they want an equation sheet. So we actually want you to make the equation sheets, right? That's why we've had on the exams before a note sheet. So you should probably still do that even for a 24-hour exam. All these equations are in the book, right? I know there's a lot of stuff in the book. They're also in the slides, which you have access to. And we want you to synthesize that and put that together, right? In a way that makes sense to you, right? If I just give you a ton of equations, that leads to the bad strategy that we see sometimes people doing, where they just try to grab something off an equation sheet and hope it works. Okay. Okay, back to springs. All right, so springs. Now about the springs, it depends. You can actually get a bigger force from a spring when you stretch it or compress it, the more you do it. And so this is actually, it's actually linear in the displacement. So there's a constant that we usually write as K. And K is just the spring constant. It depends on the actual construction of the spring. But what this means is essentially you always get the same force from the spring no matter, however you get to that displacement. And so you also get a conservative force. And then essentially you can find the work done by the spring by doing the integral, and that gives you the potential energy in the spring, right? And so this was stored, and so we can also write a U for the spring, and it's 1/2 K times delta x squared. And so we'll use this a lot because it's nice, because it's another force that we can do that's conservative. For this, you basically have to choose the 0 of your coordinate, not arbitrarily, but as the natural spring length. And this potential is then always positive. You don't get plus and minus. Okay. Other types of potential energy. The previous two examples are the ones we're going to use in this class. You should probably know that there is other forms of energy out there. And that you should be able to recognize what's going on with them, right? There's electromagnetic potential energy like you'll have in 212. You can have chemical energy, like if you have a bunch of rocket fuel and it explodes, that provides a lot of energy, right? A lot of things going flying have a lot of kinetic energy. We can't quantify these with an easy formula. So for us, they're not really potential energies in that case. And so they don't go into a U, so that they would be basically a non-conservative force. Because the extra information is that really in reality, energy is always conserved, okay? But when we're doing problems in the class, we don't keep track of it. This is like what we said with momentum as well, right? You had one system that you cared about, and momentum of that system was conserved if there was no external force causing the momentum to change, right? But in reality, that external force is coming from some other object, which gets a Newton's third law force and picks up the lost momentum or gained momentum, right? And the same is true for energy, but we don't want to keep track. We can't keep track of it unless it's basically one of these forms of kinetic or potential for our system. And so that means if you're doing a problem and you need to figure out if energy is conserved, it's a little bit more complicated in some sense than the momentum problems, okay? So you kind of have to think about a few different ways, a few different ways you might answer the question with a yes or a no, okay? So the first is, are the only forces acting conservative? So if it's the problem we did with the object getting thrown in the air, and the only force was gravity, right? In that case, gravity is a conservative force, so the energy is conserved. If there's another force acting on the combined system, it has to be like what we just did with the pendulum, right? If that net force does work, it'll add or subtract energy from the system, and then energy is not conserved. But if in the case of the tension in the pendulum, it does no work, like that, or the normal force when you're sliding on a track, then you can still conserve energy. You also need to check if there's other dissipative forces like friction acting even between the objects in the combined system. So like if you have a collision of two things, okay, can we just hold up with the questions about like the class until the end, maybe? Yeah, thanks. Right, so we had the example, right, of something collided, like two cars collided. You probably did this in the lab, I think, if you got to the lab before. If the cars collided and stuck together and stopped, right, you're obviously losing their kinetic energy. Right, so they had it at the beginning and they stuck together. So if things are getting deformed or they're sticking together, automatically you know that you have some sort of dissipative force, something like a friction inside the system, and that's going to lose energy. The last one is actually, we will have a word, a special word that indicates energy conservation, which is that if you have an elastic collision, you know you're going to conserve the kinetic energy. And so you kind of have to go through this checklist. So what I'll do is actually, I have one more poll question, and then we'll probably take 5 minutes, since there's a lot of questions about what's going on with the class that we, I guess, didn't get to at the beginning. Okay, so here's the poll question. So it's about throwing a rock. So if you have a rock and you want to throw it, probably doesn't matter which way you throw it, you basically give it the same velocity, same magnitude of the velocities, the same speed. And if you just forget about air resistance, if you throw it off the bridge, which way should you throw it if you want it to have the highest speed when it hits the water? Up, straight ahead, angled down, or it doesn't matter. So why don't we have a poll for this? All right, why don't we just take a few more seconds? Because I did say I wanted to have a few minutes for questions at the end. So. All right, 3, 2, 1. All right, we have a very mixed response here. Okay, so a lot of people think A and a lot of people think C. Not so many people B, and a decent amount also D. So let's try to think through this. We don't have a lot of time, unfortunately, because it is an important one, but let's think through what's the same and what's different about all the answers. So the first thing to think about, okay, we're going to think about this in terms of the energy, right? Because the only force acting on the rock when it's in the air is gravity, which is a conservative force. So we know the energy is going to be conserved, right? That was from that. Is the kinetic energy any different depending on the different ways you throw it at the beginning? That's the first question. First thing to think about. What's the initial kinetic energy? Right, it's the same because kinetic energy doesn't care about what direction something's going. It only cares about how fast it's going. Right? And so no matter which way you throw it, if you can always give it the same speed, right, you always have the same kinetic energy. And we're asking you about the highest speed when it hits the water. So again, that's saying which one has the most kinetic energy at the end, right? Right, but the kinetic energy at the end, right, plus right, kinetic energy plus potential energy I want this. So if I solve for that, it's just kf is ki plus ui minus uf. Right? So they all have the same initial kinetic energy, right? And so all that matters to get the final is the difference of the potential energies from gravity before and after, right? But they all go, if you release it from the same height, then it always goes down to the same place. And so the change in the height is always the same, right? So the only difference actually is if you're thinking about the throw in terms of where you release, how high you release. Otherwise, it doesn't matter. If you released in the same place, it wouldn't matter at all. So in some sense, the answer is supposed to be D, right? Now, if you were thinking about, oh, my hand is higher up when you release it, if you throw it up, then okay, I'll go with angled up as also an okay response. Because in that case, yeah, you actually gain by the fact that you release it higher up. And so you actually gain more gravitational potential as you go down. But it doesn't matter in particular the angle. Because what happens is in the different ones, it'll change the angle that it hits the water, right? But it won't change really the speed that it hits the water. Okay. Any more questions? I want to unfortunately cut that off because if there were a bunch of questions about the class. Are there more questions about what's going on with class before in the last 2 minutes? Otherwise, you can catch us sometime out. Logging in as a guest should not be a problem. Actually, I think all regular participants have the same permissions as guests for this session. Oh, okay. Martin has a question about this problem. Why is flat the same velocity? Because the point is that no matter which way you throw it, you're releasing with the same velocity. For recitations, okay, there is recitation tomorrow. There's a recitation session on Blackboard Collaborate for every time that recitation happened. So you should go to that. If you have a group of people you like to work with, you can coordinate going to the same one. We're being more flexible about time. Otherwise, try to go to the time you would normally go to recitation on Wednesday. We're going to split you up into small groups. The TAs will go through this in more detail at the beginning of tomorrow. But we'll split you up into small groups and you'll work on the problems like normal, as well as normal you can. Okay, another question about the rock though. If you throw the rock up, it falls from a greater height, right, at the top, but at that top it has no kinetic energy, right? And so it has to gain back all its kinetic energy when it gets back to the same level as where you threw it. And then it gets faster after that. Right, exactly. So because we did this in projectile motion, right? That the velocity when it on the way down and the way up at the same height was the same. And now we can think of that in terms of energy, that you get the same kinetic energy at the same height. Well, we don't take attendance in lecture. So for recitation, we actually want you to give a little short response on Blackboard saying what you did. So even like, because we also want to accommodate people who literally can't attend the online recitations because they're in like the wrong time zone. All right. Well, otherwise, if there's not more questions about stuff, yeah, you're all free to go. We're out of time. So thanks for coming, and I'll see you again next time. Recitation material will be on the website, like it has been, and so it should. Actually, I think it's already up there. Will we have a yeah, no, so yeah, we'll have a review just like we've had before. I mean, as much as possible, we're not changing the class. So we'll have review sessions before the exams and stuff. It just has to be online now.